we're ready to go. We're talking about quadratic equations last time. Let's actually finish that discussion. What do we want to do? Let's talk about completing the square. So, steps 1. So you're going to complete the square for something that looks like ax squared plus bx plus c. Make sure the coefficient of x squared is 1. If not, factor out the a and do the following inside the parentheses. You're going to add and after the linear term. The linear term is the bx term. We usually call that the linear term because it has bx to the first power. You're going to add and subtract something at the same time. That way you're adding 0, you're not changing the value, you're just going to make this thing convenient. You're going to add and subtract the following. 1/2 times the coefficient of the x. In this case, this will be b or b over a if you had to factor out the a, and you are going to square this. Now this is just taking advantage of a pattern that we noticed with completing the square. 3. Once you do this, the first 3 terms will be a complete square. Accurate. That means you get x plus something times x plus the same thing. You can write it all as x plus that thing all squared. Or here you probably want to simplify, but keep the complete square. So don't multiply out the square after you've created it. That is the completing the square algorithm in 4 steps. And basically it's taking advantage of a pattern that we notice. If you were to take x plus, let's call it b all squared, this multiplies out to give us x squared plus 2bx plus b squared. And what you would notice is that this guy here in a complete square is equal to 1/2 the coefficient of x all squared. Notice that the coefficient of x here is 2b. You take half of that, you get b. Then you square it, you get b squared. This is always going to be true for any complete square. So what we do in order to complete the square is we force this to happen by adding this kind of constant term. And by subtracting it again, we don't change the value, and it allows us to factor the first 3 terms, kind of like that. So We will be practicing completing the square with particular examples when we start dealing with circles. So for now, I'm not going to do any examples here. I am going to prove a general formula though using completing the square. So let's actually do that. Now, suppose x squared plus bx plus c equals 0. Here is not equal to 0. So that is a quadratic equation. Now, just so that I don't have to worry about whether the coefficient of x squared is 1, because we need that to complete the square, I'm going to factor out the a. Now, I'm going to do what the completing the square algorithm says. I'm going to have x squared plus b over a x. What I'm going to do now is I'm going to add a half the coefficient of x squared, a half of b over a is b over 2a. I'm going to square that, then I'm going to subtract that thing. So I add and subtract the same term. Now what you have is going to happen here is that the first three terms will be a complete square automatically. In fact, it is going to be x plus the guy inside the parentheses, all squared. It'll always be x plus the guy inside the parentheses. Now here, I would have b squared over 4a squared plus c over a. And we get that. So that's where the completing the square comes in. I turned this guy into a complete square. And you can check for yourself. If you were to multiply this out, FOIL it out, you'll actually get these three things right here. Because I took advantage of this pattern. So now, at the moment you might not realize it, but very soon you will, that it's going to actually be easy to solve for x in this situation because I've essentially created a situation where the x appears in one term. So I can kind of solve it like a linear equation. First of all, what I can do is I can divide both sides by a. Because a is not 0, so I can divide by it. So what I end up having is that x plus b over 2a squared is going to be equal to e squared over 4a squared plus c minus c over a by just moving this to the other side. I can create a common denominator here, so let's actually do that. What's missing from here is a 4 and an a, so I'm going to do that. So what you see we have now is b squared minus 4ac all over 4a squared. This is equal to x plus this squared. What I'm going to do now is I'm going to take the radical of both sides. Of course, that's going to give me a plus or minus over here. Plus or minus. And we know that the laws of radicals, laws of exponents tell us the radical of a division is the division of the radicals. So I have the square root of b squared minus 4ac all over the square root of 4a squared is going to be 2a. So now what happens is I can solve for the x by moving this guy over there. That's minus b over 2a plus or minus the square root of b squared minus 4ac all over 2a. And now I have two fractions where the denominator is the same. I can combine them by adding the tops. And this means that your x is equal to minus b plus or minus the square root b squared minus 4ac all over 2a. This is known as the quadratic formula. It allows us to solve any quadratic. You might get complex numbers if what's under the radical is less than 0. And for us, we just ignore these, but there are contexts in which those solutions would be important. That's what it's called. That is if ax squared plus bx plus c equals 0 and a is not equal to 0, then your x is going to be minus b plus or minus the square root b squared minus 4ac all the way to a. This formula was derived by completing the square. So if I ever ask you, what's the quadratic formula? Like on a quiz or something, you're going to write that formula down, which I assume most of us know already. But this is where it came from. It came from completing the square. Now, when would we need such a thing? Let's pick up back on the previous examples. So we did A and B already, so let's move on to C. This is just the list that we had last time. In the first situation, we solved x squared plus 5x plus 6 equals 0, and in the second situation, we solved 5x squared equals 20x, in which case I told you that dividing by the x is not something you want to do. Bring everything to one side and factor. Then the next situation was this guy. And the last situation was this guy. So, C. Alright, tell me how you do this one. Yeah?
Subtract. Break 13 on the other side. So,
Okay. Now, something that I see all the time, it might seem crazy to some of you, is that to set this equal 13 and that equal 13 or something like that. Doesn't work, right? Remember, if you want to set a product equal to something on the other side has to be 0. It's called the zero factor property for a reason. So we're not going to do that. Instead, we're going to follow the procedures and bring everything to one side. Okay, now that that's to one side, what do we do now?
I mean, I FOIL.
Right, multiply out. So you're going to have x squared plus 5x plus 6 minus 13. And so you would have x squared plus 5x minus 7. And what would you try now?
For my variables a, b, c equaling 1, b equaling r.
Well, the first thing you should try is try to factor, right? So you're going to do x, and now you try to think of two numbers that when you multiply them you get minus 7, when you add them you get 5. Minus 7 is odd, is prime, so the two obvious candidates are 1 and 7. But if you put a 1 and a 7 in either order, the 7x and the 1x, you can't use those to get the 5x. So what you're going to realize quickly is that it doesn't factor, at least not, doesn't factor by previous methods. Technically you can factor it, and the factors are just going to be something ugly like that, but it doesn't factor by previous methods. So now, when it doesn't factor, what we do is, use a quadratic formula. The quadratic formula didn't care whether this factored or not. It could work for any quadratic. So what we're going to do here is notice that here you have your a equals 1. The a is the coefficient of the x squared. Your b equals 5, and your c equals minus 7. So that's the ax squared plus the bx plus the c. And notice that I took the minus 7 because in the formula there are plus signs. So you think of this as a plus minus 7. And then what we have is by the quadratic formula. which you probably don't even have to write out this statement. Just realize that something can't factor, and then you immediately jump into the quadratic formula. Write a quadratic formula. You would be able to solve for x in this equation. X is going to be minus b plus or minus the square root of a b squared. Let's write it out. B squared minus 4 times a times c all over 2 times a. That's going to be what gives your answer. Here it's minus 5 plus or minus the square root of 25 minus plus 4 times 7 plus 28, which I don't think that simplifies. I probably would have been able to factor something out here if that does. So this is going to be minus 5 plus or minus the radical of 25 plus 28. That's going to be 53 all over 2. I want you to be aware that there are actually 2 answers here. You can have x equals the minus 5 plus the radical of 53 over 2, or x equals the minus 5 minus the radical of 53 over 2. You can just write it as that, plus or minus. Any questions? Now just to do the last one. Yeah. Huh?
Can I see what yours do?
What?
Can I explain to you what yours do?
Okay, yeah.
You can't factor in. So.
You can't factor. That's the first thing you would try, right? You always try to do that first. But then with the 1 here, it's only a 1 and a 1, and how are you going to use the 1 and the 1 to get the 8? So it doesn't factor. So now?
Just jump into the quadratic formula. So x equals negative 8 plus or minus 8 squared minus 4.
8 squared minus.
You put it into the fourth.
Yeah, 8 squared minus 4 times 1 and another 1 over 2 times 1.
That's minus 8 plus or minus
64 minus 4.
64 minus 4. It's going to be 60.
So
Can we actually?
I got
What's 60?
radical 15 because 4 times 15 is 60.
Right, it's 4 times 15, and we know that the laws of exponents tells us that we can split the radical here. So that's radical 4 times radical 15. And just get minus 8 plus or minus 2 radical 15 all over 2. And this is just a fraction. The 2 can divide into each part. So that's minus 4 plus or minus radical 15. And that will be your answer there. And yeah, if you plug in that thing into this equation, it'll actually be true. You'll actually get 0 if you plug that thing here and here. Details left to the reader. And in terms of quadratic equation, that's all you need to know. Either know how to solve them by factoring, which is always what you would try first. And if it does not factor, you fall back on the quadratic formula. Technically, completing the square is another method, but completing the square is just the road to getting to the quadratic formula. So you might as well just use the quadratic formula. But don't think you can forget about completing the square because there are other reasons why we'll need it. So still know how to complete the square. So I gave you the steps for a reason. But that's basically it with solving quadratic equations. Bring everything to one side, factor according to either a pattern or the AC method, and if it doesn't factor, use the quadratic formula. Let's talk about equations with radicals. We also need to know how to solve those. Let's look at the algorithm. 1. So I already gave you guys last time the basics of solving equations. You can do those 4 things. You can multiply or divide both sides by a number. You can add or subtract the same thing from both sides. You can use the zero factor property. And in some cases, which this is going to actually tell you what the nuance is, you can raise both sides to a power. But oftentimes solving the radical means you're unraising things to a power or raising them to a fractional power. And so there are issues that can happen here. So we want to be very careful with these kinds of equations. Processes, necessary. Sometimes you might have a form where it might not be necessary to move anything, but isolate all radicals on one side. Put everyone else on the other. So you're not going to actually bring everyone and get 0 right away. First thing you want to do is you want to isolate the radicals. So bring everyone who has a radical on one side, put everyone else on the other side. 2. Now you're going to raise to a convenient power. To kill the radical. So for example, if your radical is a square root, squaring both sides is going to be a convenient power. You're going to want to raise both sides to the 2. If there's a cube root, cubing both sides would be convenient. Raise both sides to the 3rd power. 3, not all of them will actually succumb to doing this once. So rinse and repeat as necessary. Until all radicals are gone. Solve the resulting equation. Previous methods. Factoring and using the zero factor property, or if it's a quadratic, you use a quadratic formula or anything like that. Stuff that we talked about between last class and this class. There's also an important step 5 here. Check your answers. The act of exponentiating can introduce fake solutions. We call these extraneous solutions. That's because of how certain powers work. If I were to square both sides, it will turn negatives into positives, and sometimes that act creates something that shouldn't be. So you do want to make sure that you check all your answers. So once you do this, especially if you're doing it several times, you'll get some ordinary equation, which you solve it using a method that I told you about before. You'll get a bunch of answers. What you need to do is take each answer, plug it into the original equation, the one that has the radicals in it, and see, does this equation make sense? That's what I mean to check your answers. Plug answers into the original equation. Before you start doing anything. And check that they make sense. start raising both sides of powers, you potentially introduce extraneous solutions in certain situations, especially when you're raising to an even power. That's kind of the process. Pretty much if you're given an equation with radical, your first goal is to get rid of all the radicals. You do this by isolating them and then keep raising things to powers until all the radicals are gone. Then you'll get a regular equation, solve it using the previous methods, and make sure you check your answers. Let's do some examples, because not much is by way of theory besides that. Hopefully we'll be able to get all the nuances that can happen here with those. Nothing too crazy, I'm keeping them with the square roots, but the principle would work with cube roots or anything else. Okay, first step. Square both sides, right? So step one would be kind of to isolate the radicals. It's already isolated, there's only one side of the radical. So what you're going to do now is you're going to raise it to a convenient power. Since this is the square root, squaring is going to be the convenient power. So this means that our 8x minus 1 will equal to 9. I will then be able to move this over, that'll be 10, and so then I'll get my x is 10 over 8, or in other words 5 over 4. Now before I box that answer, I am going to check it. It's very important, because when I square, I could turn negatives into positives and so on and so forth. So I'm going to check. I am going to take the radical of 8 times 5 over 4 minus 1. This is the radical of, this will cancel into that 2 times 10 minus 1. This is radical of 9, which is 3. And the original equation, the other side was 3. So that checks out. And yeah, that's my answer. X equals 5 over 4. Solves this equation. Here's a situation in which the if necessary to me is not necessary, because you'll actually do yourself more harm than good isolating the radicals to one side, because then when you square you have to expand out, you'll actually recreate another radical while getting rid of 2, so you take 2 steps forward, 1 step back. In the case where both sides are just radicals, instead of isolating them, I would just raise both sides immediately. So I would square this here. Now bringing them to one side and squaring is still going to work. It's going to just take you longer. So squaring both sides, you then obtain 3 plus x equals x squared plus 1. All right, there are no radicals in this equation. How do I solve it? So bring the x over, bring the 3 over, we get this. Does that factor? X minus 2, x plus 1. So my x can either be 2 or x can be negative 1. Now I need to check that both of these actually work. Over here, check. X equals 2. Then I would have the radical of 3 plus 2 equals radical of 5. That's the left-hand side. And the right-hand side would be the radical of 2 squared plus 1. That's also radical of 5, which is the right-hand side. So this one checks out, and this is a part of the solution. Then I would check x equals minus 1. I mean, the radical, 3 minus 1, well, that's just radical 2. That was the left-hand side. If I plug in minus 1 in the right-hand side, I would get minus 1 squared plus 1. That is also radical 2. That was the right-hand side, so those are the same. And yeah, both of these actually work. Any questions on anything so far? Okay, what do we do now? Square both sides. Radicals are already isolated. So if I square this, what do I get? 1 plus x
Plus 1 minus x
1 minus x.
equals 4.
No. What's wrong? Do you guys realize what you did? Realize what you did? The thing that Jhevon told you first class, never do. Or it's like, kill you! You just distributed the power across a sum. You just squared this and squared that. That is not how we square something. What's the correct answer? Why are we so iffy? Okay, let's start with the basic. What is the formula that we want here? What is that equal to? A squared? No.
Wait.
Plus 2a.
Wrong.
That's what we want. So we're going to square the first thing. We're going to multiply both of them and multiply by 2. And then we're going to square the last thing. This is how you square something. Don't forget the rules just because things look weird. The rules must be obeyed at all times. That's how we square something. Square the first thing, square the last thing, multiply them together, and multiply by 2. You add all these together, that's how we square. Now we can clean up. Notice that we raised both sides to the square, but we didn't completely get rid of the radicals. So what do we do now? Well, rinse and repeat. Isolate them again, and then actually square it. So what I would do here, by the way, the laws of exponents tell me I can put these both under one big radical, multiply them together. What would I get if I multiply those together? X plus 1 times x minus 1. 1 minus x squared, difference of squares. So what I'm going to do now is I'm going to move everyone else to the other side. The 1 plus 1 is 2. Move that to the other side, that's minus 2, so this is 4 minus 2, which is 2. Then I would have x minus x, so these x's actually die. and I end up with that. I can divide both sides by 2. And now I'm in a situation where the radical is isolated. Yeah?
Did you tell me we have 2 radical, 1 plus x, 1 plus x? Tell me we got that again.
This line here?
Yeah.
Because this thing here, it's like your a plus b squared.
Okay.
So it's going to be a squared plus 2 times the a times the b plus the b squared. So now I divide both sides by 2. Radical is isolated, so I'm going to square again. So this is the situation where we have to ring some repeat. Now I square again, I get 1 minus x squared equals 1. And so what that actually means is that move x squared to the other side, I get x squared, subtract 1 from both sides, I get 0. So what does it mean that x squared equals 0? X must be 0, right? Technically you can factor this and say, oh, this is x times x, and then 0 factorial, x is 0 or x is 0, or x is 0, right? And so now what I do is I check. There's only one thing to check here. If I plug in 0 for x, does that make sense? Well, I'd have the radical of 1 plus 0 plus the radical of 1 minus 0. That's just radical 1 plus radical 1. That is 1 plus 1, which is 2. So that actually checks out, and this is actually my answer. Yes, be careful with the glass ones. At the time it looks, it probably looks simple, like a lot of you probably rolled your eyes at me. Of course I know not to do that, but it sneaks up on you. Sometimes you have things that look differently, and you just, your brain just decides to get rid of things in a not so good way. Yeah.
Why did you go from 4 to 2?
Oh, I'm isolating the radical. So I bring everything else to the other side. So it's the 1 subtracted, the 1 subtracted, so it's 4 minus 1 minus 1, that gives me the 2. The plus x and the minus x, those actually kill each other, and so I just have this left over. Then I divided both sides by 2, and then I squared both sides to get rid of the radical again. Okay, well, let's try the final one. What do we do here? I probably isolate the radical first. This 1 has nothing to do with that radical. Get him out of there. Now I would square both sides. Potential mistake here is people just leaving the negative sign. The negative sign is a part of the thing that gets squared. So what I have now is 2x minus 1. I'm not going to write that squared again. Let's actually just square it out. What is this squared? 4x squared minus 4x plus 1, right? Using the same a plus b all squared formula. Here, the square of negative 1 is just positive 1, and the square of that is 2 minus x. So that's the situation we end with. How do we solve this? Yeah. Add x, bring everything to one side, in other words. If I add x, I would have minus 3x. If I subtract 2, I would end up with minus 1. Look at that. Yeah.
-1?
Come again?
Why don't you divide by -1? Moving everything over.
It wouldn't have made a difference. Had I done that, this would be plus, that would be plus, this would be minus. This line would be exactly the same. You could do that, but it wouldn't make a difference here. Because when we're squaring, so the negative sign is not going to really matter. What about this? How would you solve this? Does it factor? Oh, into what? Yeah, to get a 3, I probably need a 4 and a 1. And to get the 1, I need 1s here, so I have 4x and 1x. Can I get to a -3? Yeah, make sure it's a +1 and a -3. -4. That will give me the -3. So that factors. So now we have x is equal to -1/4 or x equals 1. Now we go through and we check. So let's check the x equals -1/4. If I go back to the original equation, then I have 2 times -1/4, that's equal to -1/2. That was the left-hand side. What about the right-hand side? I would have 1 minus the radical of 2 minus -1/4. This is going to be a little bit of arithmetic here. So this is 2 plus 1/4, or in other words, it's going to be the radical of 9/4, which is going to be 1 minus 3/2, which is going to be what? Right, this is 2 over 2 minus 3/2, that's -1/2. Right, that actually checks out, so this is an answer. Now check. You know what? I'm noticing a pattern here. Every example you get in class, it always checks out. I don't have to check, right? Okay, let's do this one. 2 times 1 equals 2 would be the left-hand side. 1 minus the radical of 2 minus 1 is going to be 1 minus the radical of 1, which is 0. This one does not check out. I have to make sure I gave an example like this. I don't want you to have the assumption that it's always going to check out. It doesn't. This is actually not a solution. This is what we call an extraneous solution. Some extra solution induced by the squaring. It's actually not real. It's a figment of your imagination. So that actually does not check out. So the only solution to this radical equation is x equals -4. That finishes all the lessons we need with radical equations. Pretty much that's the idea. Keep isolating the radicals and raising them to powers until you don't have any more, and then you kind of use the principles that we learned from the last class. Let's talk about a different kind of equation. And this again, I'm gonna do just like one example, because once you know how to solve equations in general, this is just one extra situation where you just have to be careful of how you're applying those principles. Equations with absolute values. Recall the absolute value of x equals, what is this equal to? put that in a quiz once, and a lot of people wrote absolute value of x in words. That's not a definition. That's just what its name is. What is it defined as?
X greater than X greater than 2, but from X equals 0. X is greater than 0. It's that fancy bracket thing, and then you get that X is, when X is less than 0, it's negative.
It's
I mean,
negative
it's
what?
positive. It's when X is negative, it's positive. It's positive on both sides. I forget what the.
Is equals to x when x is greater than 0?
It's the first line. Then
It's equal to 0 when x is 0.
and the last line.
It's equal to negative x when x is less than 0.
Yes. You guys need to know the definitions, the mathematical ones. It's very important. If you don't know what something is, why would it not be easy to confuse you in a problem? Right? You see an absolute value in an equation, you just freak out, you don't know what to do because you don't know what it is. You know all the definitions. That is the definition of the absolute value. So what that means is the thing inside of this, it can be negative or positive, but this thing forces it to be non-negative. Now, what does that mean for us? Well, simply put, the following would hold. If you have something like the absolute value of A equals B, where these guys are just some mathematical expressions, right? They could have whatever kind of function. This is an expression, and this is some other expression. What you realize is that this, because of how absolute values are defined, it's going to break this thing up into two cases. In the event that what's inside is positive, the absolute value, positive or 0, the absolute value is not going to do anything. It's just going to break down into the equation A equals B. And this is for A greater than or equal to 0. That's going to be what happens. However, if what's inside the absolute values is negative, you will have minus A equals B will be the resulting equation because of the definition. So an absolute value equation breaks up into two separate equations without absolute values. So when you see an absolute value equation, all the principles we know about regular equations still apply. The difference is that one equation branches off into two separate equations. And then you pretty much solve them one by one. They'll be very similar to solve because it's just a sign change on one side. But it is two separate situations that need to be considered. So let's just do one example. There's nothing to talk about here. Let's say I had the absolute value of 2x plus 1 equals 3. Then basically what's going to happen here is you have two cases. Then you would have 2x plus 1 equals 3. This is if the 2x plus 1 is greater than or equal to 0. Or in other words, your x is greater than or equal to minus 1/2. So in the event that your input is greater than or equal to minus 1/2, that's the equation you want to solve. Or you'd have minus 2x plus 1 equal to 3. And that's if your 2x plus 1 is less than 0, or your x is less than or equal to 1/2. So all you do now is solve these two equations, and they're both linear equations. So now it could have been a quadratic, could have been something else, but in either case, whatever equation you end up with after removing the absolute values, you solve it based on previous principles. So in the first case, we would have, bring the 1 to the other side, we'd have 2x equals 2, which implies that x equals 1, or we'd have minus 2x minus 1 equals 3, which means that minus 2x equals 4, which means that x equals minus 2. What? And now what we can do is we can check both. If I were to plug in 1 here, I would get 2 times 1 plus 1. So it's 3 on the inside. Absolute value of 3 is 3. So that checks out. And if my x equals minus 2, plug in minus 2 here, I get 2 times minus 2, which is minus 4. Add 1, I get minus 3. Take the absolute value of minus 3, I get positive 3. So this also checks out. So yeah, your x can be 2 things in this case. So at first it looks like a linear equation, but the absolute values actually make a difference. If you just ignore them and solve it as a linear equation, you only get one of the possible answers. So you just have to be aware of how the absolute value actually functions, what it means to be an absolute value. It means you branch into 3 potentially different situations. You have to account for all of these situations. In principle, nothing else to teach you. Which brings us to the last kind of equation, which again, there's not going to be much to teach you. Once we covered what we learned in last class and we understand the principles very well, all the other situations are kind of, it's just like you start the problem by doing something else to just put it in a convenient form, but you finish up by doing the kinds of things that we were doing last class. And these would have helped you with the bonus problems on the quiz, I guess. Equations with rational expressions. So not radical expressions, but rational ones. This means you have things where you have divisions and functions are in the divisions. Again, dealt with similarly. But the difference is just multiply both sides by the LCD before proceeding. I already told you guys what the LCD was. I assume we all know how to multiply both sides by something. So let's just jump into examples. We solved equations like this, similar to this last time. Let's throw one again for good measure. B. Where we had something like 1/2 equals minus 3 over x squared minus 10. Now, as long as you're not dealing with a simple equation, I would still do our due diligence here and check your answers. Because again, now that there's divisions, there are certain things that you don't want to happen. For example, here you don't want x equals 2. So if you solve it and you get x equals 2, rather you throw that solution away. Similarly here, I don't want x equals plus or minus radical 10. So if those pop up, I have to know to throw them away. So you definitely also want to multiply through by the LCD to turn things into a simple equation, but just understand, sometimes you solve it, you'd have extraneous solutions. Try these, we'll pick up with them on Wednesday, and actually move to inequalities on